All right, let's dive right in. We're talking about a scientific breakthrough that could genuinely reshape our world. And it all starts with a problem you deal with every single day, even if you don't realize it.
I mean, really think about it. When a power plant generates electricity, it's got to travel miles and miles of wire just to get to your light switch. But here's the thing, that journey isn't perfect, not by a long shot. So what's the toll? Just how much gets lost along the way?
8%. And look, that might not sound like a crazy high number at first, but when you scale that up across the entire power grid, we're talking about a colossal amount of wasted energy. It's like this giant invisible leak in our whole global energy system, just happening 24/7.
And this really drives home the real-world cost. Professor Ching-Wu Chu, and he's a huge part of this story, by the way, is basically saying, look, if we plug this leak, it's not just about being a little more efficient. We're talking billions of dollars saved, and a massive win for the environment. So how do we actually plug it?
Well, for more than 100 years now, scientists have been chasing this dream, kind of the holy grail of physics, really. And that's the search for a perfect conductor. Which brings us to the absolutely incredible world of superconductivity.
So what is superconductivity? Well, it's this amazing property that some materials have where electricity can just flow through them with absolutely zero resistance. I mean zero. No friction, no energy getting lost. The power that goes in is the exact same power that comes out. That's the magic right there.
And the difference here is just stark. A normal wire, right, it's like a leaky pipe. You're always losing energy, usually as heat. But a superconductor, that's a perfect pipe. Nothing is lost, it's perfect transmission. But, as with most things that sound way too good to be true, there's a catch.
And oh, it's a big one. For decades, this amazing superpower would only show up at temperatures colder than deep space. I mean, you needed incredibly expensive liquid helium just to cool things down. And that has been the single biggest wall stopping us from, say, building a perfect power grid with this stuff. So this challenge, it kicked up this incredible scientific quest that's been going on for a century. A race, really. A race against the cold. To find a material that could superconduct at warmer and warmer temperatures. To finally bring this tech out of the super specialized lab and into our world.
But progress was slow. In fact, when we talk about the kind of superconductors we really need for practical stuff, the ones that can work at normal, everyday atmospheric pressure, the record was just stuck for over 3 decades. The whole field was basically hitting a wall.
Just look at this timeline. Back in 1987, a huge leap forward. Then, in 1993, another team sets a new record, 133 Kelvin. And then, crickets. For more than 30 years, that was as good as it got. At normal pressure, anyway. Until now.
Because, just recently, that long-standing record wasn't just broken, it was absolutely smashed. Yep, researchers at the University of Houston have just hit a massive milestone in this century-long quest.
This is the new number to beat, minus 122 degrees Celsius. Now, let's be real. That is still incredibly cold, but it is a huge leap forward in this race against the cold.
So in scientific terms, that's 151 Kelvin. And here is the really crucial part. This is now the highest temperature ever recorded for a superconductor that doesn't need to be under constant crushing pressure to work. And that makes it so much more practical.
So let's just recap the key details here. The team at the University of Houston's Texas Center for Superconductivity, led by Professor Chu and Dr. Liangzi Deng, they're the ones who did it. And the real significance? They made a stable superconductor at ambient pressure. That is a game changer for getting this stuff into the real world. Okay, so the big question is, how on earth did they pull this off after the record was stuck for 30+ years? Well, the answer lies in this really clever, innovative technique, and they actually borrowed the secret from a totally different field.
It turns out they used a method called pressure quenching. And if that sounds a little familiar, it might be because a similar process, applying intense pressure and temperature, is used to create synthetic diamonds. The Houston team was the first to figure out how to successfully use this idea to kind of lock in that high-temperature superconducting state.
Okay, so here's how the process works in 4 key steps. First, they squeeze the material under insane pressure. This enhances its superconducting properties. Second, while it's still being squeezed, they freeze it. Third, they rapidly release that pressure. And finally, and this is the magic step, that high-temperature superconducting state gets locked in. It stays stable even after all that pressure is gone.
So, where does this all leave us? I mean, this new record is a monumental achievement, a genuine milestone, no doubt about it. But what does it really mean for the bigger picture, for that dream of a perfect power grid?
Well, the reality is, while this is a massive win, the ultimate goal, what scientists call the holy grail of room temperature superconductivity, well, we're not there just yet. We've taken a giant leap for sure, but the journey isn't over.
This chart really puts it all into perspective, right? You can see the old record, down there at 133 Kelvin. And then you see the new record pushing that boundary up to 151 K. That's fantastic progress. But then you look way up there, and you can see the gap that's still left to get to room temperature, around 300 Kelvin. Closing that gap, that's the next great challenge.
But here's the thing. This achievement proves that new ideas, new methods can shatter old limits. It breathes new life into this whole quest. It brings us one giant step closer to a world without that 8% energy leak, a world of perfect transmission. The question isn't really if we can close that gap anymore, it's what will our world actually look like when we finally do?